At the end of week 2, we started to define the derivative. And we're going to be looking at the derivative and many of its properties for about 2.5, maybe 3 of our 6 weeks. So right here, we're going to look at a couple properties of the derivative. And for this, you don't necessarily need to know any derivative computations. We will look at 2 of them, but they're fairly straightforward. During week 3, in our Wednesday meeting, we're going to look at some more. If you're doing this after that, we looked at some more. But for this, let's recall what the derivative is and what we defined it to do. Recall the derivative. So we have a function, f of x. We're creating a new function, f prime of x. We're defining a new function, f prime of x, to give the slope of the line tangent to f of x at each x value. So the derivative, this new function f prime of x, where that prime looks kind of like a big apostrophe, the derivative f prime of x of the function f of x is defined to give the slope of the line tangent to f of x at each x value. So the derivative takes any x value as its input and throws out as its output the slope of the line tangent to f of x. But to define that, we used a limit. Recall, f prime is defined by this limit. F prime of x equals the limit. We started with a limit which gives the derivative at a point, and then we essentially rewrote that in a more usable way. I'm going to write this a little smaller so it fits there. But f prime of x was defined as the limit as h goes to 0. That's an h, a lowercase h, of f of x plus h minus f of x all over h. Remember, to get this, we took slopes of secant lines, but then used a limit to let the secant line approach a tangent line. Now, what do we know about limits? Well, we know a good deal about limits. One thing we know is that a limit can exist, or a limit may not exist. Right here, we're going to look at what it means for a function when this limit exists and when it doesn't exist. So let's say, let's say it here. Observe, this is a limit, so it may not exist. This limit may not exist. The variable in this limit is x. So this limit may not exist for some x values, let's say. For some x values. And what does this look like? Well, we'll see. We'll actually see 3 cases. But to get there, let's start with this definition. We say a function f of x, the function f of x, is differentiable if f prime of x exists for every x in the domain. So we say f prime of x is, we say f of x is differentiable if this limit exists in its entire domain. We say it's not differentiable if there is at least one x value where the derivative does not exist. Differentiable means the derivative exists. And there's a fairly large theorem in math relating differentiability to continuity. And the theorem says if f of x is differentiable, meaning if the derivative exists on its entire domain, then f of x is continuous. If f is differentiable, then f is continuous. So all functions where the derivative always exists can be drawn without lifting your writing implement. A proof of this theorem is not difficult. It's a little It is in the textbook. It's a little tedious. There's a step where you multiply by 1. There's a step where you add 0. I'm not too concerned with that. What's far more interesting for our purposes is the converse of this statement. So this theorem says, if something, then something else. So if A, the first thing, then B, the second thing. The converse flips that around and says, what about if B, then A? If the second thing, then the first thing. Is that true? Well, I didn't write the theorem in a way that also suggested that that was true by using an if and only if statement. So you may suspect if I flipped these two words around, then it would not be true. And that is the case. The converse, however, is not, well, I'll say it does not necessarily hold. Converse does not necessarily hold, meaning the statement, if f is continuous, then f is differentiable, does not hold. And let's take a look at what that looks like. So to show the converse doesn't hold, we're going to find a function which is continuous, but not differentiable. And remember, to show a function is not differentiable, all we need to do is find one x value at which the derivative does not exist. Which function does that? Well, there are three classes of functions we could use. We'll go through the details for one of them, and then we'll go through a brief discussion for the other two. Which function? Well, this one works. Consider f of x equals, that's not going to fit on this board. It's a common function, we've seen it before. The absolute value of x, a function we have seen before. And for this, we are going to need the formal definition of the absolute value of x, the piecewise definition. That's a pretty good left curly brace. Remember, the absolute value of x is defined as x if x is greater than or equal to 0, and if x is negative, the absolute value throws out negative x. We're going to show that this function is continuous and not differentiable. So first we'll notice, well, first we'll draw the function. There's a Cartesian plane. This function, absolute value, looks like this. This is a continuous function. You can draw it without lifting your writing implement. Notice this is continuous, and notice f of x is continuous. We'll also show that this function is not differentiable. Now, where is it not differentiable? Well, if you look at this curve, you may think there's one x value at which the function behaves a little differently than the other x values. And there is. So we're going to show that this function is not differentiable at x equals 0. And if we show it's not differentiable at a point, the function itself isn't differentiable. Remember, differentiable means the derivative exists everywhere. It means that limit exists everywhere. So we will show well, let's say it like that. I could say we will show f prime of 0 doesn't exist. I'm going to phrase it a little differently. We will show f prime of x doesn't exist at x equals 0. We'll show f prime of x doesn't exist at x equals 0, and that'll give us what we want. Now, showing f prime of x doesn't exist at x equals 0, equivalently, we show f prime of 0 doesn't. Now, how are we going to show f prime of 0 doesn't exist? Well, remember the definition of f prime of x. I'll write the I'm going to erase this, but this is a, if I had a larger board, I would point back to what was written on this second board before. Recall the definition of the derivative. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. That's one fraction split across the board, all over h. So what's f prime of 0? Well, replace x with 0. What do we have? Limit as h approaches 0. I'm going to move this over so it... f prime of 0 equals the limit as h approaches 0. Replace x with 0. That's what we're doing. So we have f of 0 plus h minus f of 0 all over h. The derivative is defined as a limit. We are going to show this limit doesn't exist. Well, to do that, let's simplify it a little. Let's simplify it like this. Equals the limit as h approaches 0. What's f of 0 plus h? Absolute value of 0 plus h. Well, what's 0 plus h? Just h. Maybe I'll just write it like this. Zero plus h is h. F of h is absolute value of h. F of 0, absolute value of 0. Still all over h. And notice again, if you did try a substitution, h equals 0, you would get a 0 over 0. So we do have to do some algebra until the 0 over 0 cancels. Absolute value of h. Well, we don't know what h is yet. Absolute value of 0, well, 0 is a number, top line in the definition. Absolute value of 0 is 0. So this equals the limit as h approaches 0 of absolute value of h minus 0. So absolute value of h over h. So right here, we have f prime of 0 equals this limit. How do we show a limit doesn't exist? We do it, I shouldn't erase that. I'm going to do it on the top of this board. I'm going to move this definition. I can erase this. I'm going to go back to this curve in a moment once we're done with this. But that's an easy enough curve to just redraw. I'm not positive how much space what we are about to do is going to do. We're going to use. Okay, I'm just going to reference that, but I wanted to erase it. So, how do we show this limit doesn't exist? Well, when will a limit not exist? The limit won't exist when what happens on the right is different from what happens on the left. So we will show that limit as h approaches 0 from the right of that function doesn't equal the limit as h approaches 0 from the left of that. If we show that the limit as h approaches 0 from the right doesn't equal the limit as h approaches 0 from the left, then that limit doesn't exist. Well, let's show that those two limits aren't equal. Limit h approaches 0 from the right, absolute value of h over h. Let's not trip over the plug. Absolute value of h is approaching 0 from the right. H is on this side of 0. H is on the positive side of 0. The absolute value of x equals x on the positive side of 0. So the absolute value of h equals h on the positive side of 0. We haven't taken a limit yet, so we still need the limit. Absolute value of h is h on the right of 0 divided by h. how about this? Substitute h equals 0. You still get a 0 over 0, but we still haven't taken a limit. H over h reduces to 1. And as h approaches 0, 1 doesn't change. 1 stays as 1. So if we show that the limit on the left doesn't equal 1, then that limit won't exist. The function won't be differentiable. It gives us a counterexample to the converse. I want these to kind of line up. How about on the left of 0? Well, on the left of 0, these h values are, here's 0, these h values are on that side of 0. On that side of 0, absolute value of x is defined as the negative x. So here, absolute value of h on the left of 0 is negative h. This limit, we still can't do a substitution h equals 0, because we'll get a 0 over 0, but that fraction reduces to negative 1. Negative 1, which equals negative 1. So the limit on the right is positive 1, the limit on the left is negative 1. Therefore, this limit doesn't exist. So I'm just going to write over here, that work should have gone under this kind of. So I'll just say which doesn't. Now let's not write that. Let's say, therefore, f prime of 0 doesn't, or does not exist, dne. So f prime of 0 equals this limit. We simplified it, and then we showed this limit had different values on both sides of 0. Now, so therefore, this function is continuous, but not differentiable. Therefore, the converse of that statement does not hold. Now, can we see that in the graph? Now, you may be suspecting, well, the absolute value at 0 has that, corner-like point at 0, or the absolute value of x has that corner point at 0. Is that what is causing this? Well, it is. You don't have to redraw this graph. You could reference back the graph I had drawn on the second board. But why can we see that the absolute value is not differentiable at 0? Well, remember what we defined the derivative to do. If you have a pencil or a pen or something, you can use that as your tangent lines. The derivative is defined to give us the slope of tangent lines. What does that look like? Well, for a curve like this, a curve, just take a parabola and move it around, quadratic function. What do the tangent lines look like? Well, the slope of the tangent line is some negative number, but at this x value, let's say, at this x value, what is the slope of the tangent line? Well, the slope of the tangent line is the slope of that line. But the derivative, whether a function is differentiable, or how should I say it? When a function is differentiable, you are going to get a slope of a tangent line at any point. And as a consequence of that, you can kind of see the tangent lines traveling through the graph in kind of a smooth, flowing way. What do I mean by that? Well, take this tangent line at a point, and you can let that travel along the curve. So take your pen or pencil, whatever, your finger even, that can be a tangent line. If I used a marker here, I don't think that would be as illustrative. So let your writing implement, or just take a tangent line, say, over at this x value. Let that travel along this parabola. You can imagine this moving in a smooth manner. Now, what does that look like for the absolute value function? What does that look like for the right half of the absolute value function? Well, the slopes of these tangent lines all look like this. on the right of 0. The slopes of these tangent lines all look like this on the left of 0. But what happens at 0? Well, at 0, to let this tangent line travel through, notice, if you're letting these tangent lines go down, once you get to 0, it kind of has to shoot around and go all the way from this slope of -1. Once you get down to 0, flip around to a slope of +1. These tangent lines aren't traveling through this curve in a smoothly consistent manner, like they are on, say, a parabola, where the derivative will always exist. The parabola, your tangent lines flow nicely through, back and forth. On a corner function, like the absolute value, the tangent lines are going to shoot from negative to positive, or if you go the other way, shoot from positive to negative. And because of that, the derivative is not going to exist at this middle point, because it has to jerk around from a positive to a negative. Another way you could see that is on the right of 0, these all have a +1 slope. On the left of 0, these all have a -1 slope. So, one way we can see the derivative doesn't exist is by going through a limit computation and looking at both sides. We could also look at the tangent lines traveling along a curve. So right here, we have this absolute value function at 0. Let's look at 3 general classes of functions which are not differentiable but are continuous. The following curves are continuous but not differentiable. And remember, differentiable means the derivative exists everywhere. To show a function is not differentiable, we need a point at which the derivative doesn't exist. So here, these will not be differentiable because there are going to be 3 curves here. In each case, f prime at a does not exist. This is a colon, not a... I wasn't unhappy that the derivative doesn't exist, I just realized that. That's a colon at the end of this sentence, but it follows a parenthetical. Okay, great. First, a corner. So this is the generalization of the absolute value. Why does f prime at a not exist? Well, on the left of a, we have these negative slopes, and then on the right of a, we have these positive slopes. And we call that a corner function. So at a, it won't exist. The slope of the tangent line at a is not 0, because there's a point there. On the right and left, it doesn't approach 0 on both sides. These are both, like a +1 or a +10 slope, and a -1 or a -5 slope or something. But we call that a corner. Next, we have what we call a cusp. That's a really lousy drawing. We have a cusp. On the worksheet, we'll go through the details for a cusp. That's a little better. Here's A. So right here, these should all be called F since I say F here, then that's fine. Why does the derivative not exist at A? Well, notice first, the derivative exists everywhere else. On this one side, you can let these tangent lines travel along the curve. On the other side, you can let these tangent lines travel along the curve. But what happens at A? So remember, the derivative here didn't exist because we had different tangent lines on both sides. Well, on the right side of A, let's start at the right side, what are the slopes of these tangent lines? Well, positive. Let's get closer to A. Positive. So here I'm at like this x value. Closer to A. This x value. Positive. Remember, the limit cares what happens as you approach A, in this case from the right. How about even closer to A? More positive. Even closer to A. more positive. So on the right side of A, the slopes of these tangent lines, positive, positive, more positive, more positive, more positive. They keep getting more positive. You know, they could even approach a positive infinite slope. But notice what's important, they keep getting more positive on the right side of A. How about the left side of A? Well, let's start with x value way over here. Negative slope. It's slightly downward slanting. How about this x value? A more negative slope. How about this next x value closer to A? A more negative slope. Get really close to A, it's a very negative slope. So over here, negative, more negative, more negative, more negative, more negative, and they keep getting more negative, and they could approach, you know, a negative infinity. But negative, 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 more negative, or I should say negative, more negative, more negative, more negative, negative, as it gets closer to A, more negative. On the other side, positive, more positive. So on the one side of A, the limit would give you a negative number, which is getting more negative. On the right side of A, you'd have a positive number getting more positive. So traveling through A, you know, notice the tangent lines, if you tried to have them travel through the point A, you'd have to jump from here to something very positive. You know, over here, you know, it's smoothly traveling through until you get to A, where it has to flip up like that to travel through A. So that is another function which is not differentiable. Notice it is continuous. You can draw it with a, you know, without lifting your writing implement. The third type of curve, which is continuous but not differentiable, is when we have a vertical tangent. And there could be, and in my mind, there are times I find it convenient to view this as differentiable. In general, in math, it's nice to exclude infinity when taking derivatives. And what does that mean? Well, one thing it means is that I like these two examples more. Another thing it means is, you know, you may, at least somewhere in your mind, want to disagree with this result, and I sympathize. Let's make it look a little more vertical tangent. But just know, if there is some debate in your mind whether this should be non-differentiable, when we defined limits, we defined the limit to be a real number. So infinity immediately meant, a limit of infinity immediately meant the limit did not exist as a real number. Okay, that's a better vertical tangent. What does a vertical tangent mean? Well, there's our A value. At A, we have a vertical tangent. You know, one example is what? The cube root of x at A equals 0. So right here, so on the right of A, we'll do the same analysis. On the right of A, we have these slopes going up, or well, we have these slopes which are positive. As you approach A, they get more and more and more positive. On the other side of A, we have these slopes which are positive, getting more and more and more positive. So in particular, since the tangent is a vertical line, the limit on the right of A would be a positive infinity. Immediately, right there, derivative doesn't exist. But also on the left of A, we also have a limit of positive infinity. The definition for limit, or the theorem for limits, limit on the right equals limit on the left. Again, that applies only to finite numbers, because in the definition of limit, we include only finite numbers. So you could, in my mind, this should be considered a special separate case possibly. But you could see the tangent lines kind of traveling through this curve in a smooth way. in math, there are times, especially in calculus analysis in general, there are times when throwing infinity out makes future math more convenient. You know, if you take a real analysis course, like that's a 400 level math course, there will be times where throwing out infinity is more convenient. But for us, we will have these three functions, which are continuous. Notice they are all continuous, but not differentiable. I like these two more. But I do think it's important to see how the tangent lines travel through. The next result in the next video is going to be another where we look at tangent lines traveling through a curve.